Hello there, and welcome to everyone joining us for this latest IoT Central webinar. I'm Clive Maxfield, everyone calls me Max, and I'll be your host. In addition to being a practicing engineer, I also act as a technology consultant, author, speaker, and educator. I'd like to start our webinar by thanking Edge Impulse for sponsoring today's event. Edge Impulse is a leading supporter of the IoT Central community, and we're grateful to have them as sponsors. And joining Edge Impulse will be a guest from Himax. Today's webinar is entitled Building Your Best IoT Application Starts with Embedded. Before we begin, I'd like to briefly review the format of today's proceedings. The event will be 1 hour long. We'll have two presenters who I'll introduce in just a moment. There'll be a 10 to 15 minute Q&A session following the presentation. And this event is being recorded and will be available on iotcentral.io tomorrow. I'd also like to encourage you to provide questions throughout the presentation. We will be reviewing and presenting these questions on your behalf during the Q&A portion of the event. Running machine learning on embedded devices with scarce resources is one of the most exciting developments of the past few years, allowing embedded systems to perform tasks like detecting complex motions, recognizing sounds, and classifying images. To make it possible to build and run these models on the smallest of form factors, Edge Impulse has partnered with Himax to support the new Himax WE-I Plus evaluation board. In this IoT Central webinar, you will learn how easy it is to get started with embedded IoT design, understand the benefits of using machine learning on embedded devices in small form factors, and see a hands-on demonstration by Edge Impulse and Himax. So now I'm very pleased to introduce today's speakers. Jan Jongboom is the co-founder and chief technology officer at Edge Impulse. Jan is an open source developer and a technology evangelist working on TinyML. His experiences range from embedded to web and everything in between. CJ Xu is a systems engineer at Himax Technologies and is in charge of WE-I Plus system software and hardware development. So, with that, I'm going to hand things over to our presenters, Jan and CK. Over to you.
Wonderful. Thank you so much, Max. I need to enable my webcam. Sorry about that. There we go. That works a lot better. Hi, welcome. I'm Jan. As you can see here in the little video, that's CK. Yeah, let's dive straight into the presentation. As Max said, we'll kick it off with an actual presentation about why we think embedded machine learning is really important and what we can do on Himax. And then the interesting part of today is going to be the demonstration. It's going to be really killer. We're actually going to build a real machine learning model right here in this session. So look at this number, 30 billion. It's an astonishing amount. It actually sounded much bigger when I wrote down 30 billion rather than actually put all the zeros. You kind of lose track. And 30 billion, what might that number be? Let that sink in for a second. Well, lots of people here kind of understand this because you're in the IoT Central webinar, but 30 billion, this is the estimated number of processors, MCUs and MPUs shipped in 2020. There's an astonishing number of devices already going into a wide variety of products, industrial, consumer electronics, and anything in between. But also, if you think, okay, well, the billions of devices have arrived and billions of processors have arrived, what do we actually do with all of these devices? And for me, especially when I think about the typical IoT sensor, the typical IoT product, it is way too little. It's because we try to kind of solve these really easy things first. The typical IoT sensor is, well, I have a temperature value, here it's minus 10 degrees. I then use a thermistor or a digital thermometer to actually measure that. I get the value of that, and that is sent to the cloud. Lots and lots of IoT deployments don't really go further than this. I think this is the reason why literally every smart city project that I see has a kind of a parking sensor measurement or a parking sensor attached to that, because it's easy. You know, you have a magnetic field and you detect that and you see if there's a car parked, yes or no. The reason why it's easy is because, well, there's a sensor that does exactly what I need. In case of temperature sensor, I can buy a thermistor or a digital temperature sensor that tells me exactly what the temperature is. I just need to read that in and upload it to the cloud. Similar with our parking sensors. I can buy a Hall effect sensor, or I can buy a sensor that detects a magnetic field. When there's a car above me, I get a 1, otherwise I get a 0, and that's what I easily upload to the cloud. However, that really limits kind of what we can do with our IoT deployments, because there's other stuff that is super interesting, but don't really do because it's much, much harder. For example, if I have if I'm on the savannah and I want to know if I see an elephant somewhere, that is much harder. I need to make a photo of it, and someone needs to look at it and then send it off to the cloud. And why is it hard? Well, there is not a standard do I see an elephant sensor that I can buy from DigiKey and that I attach to my system. It returns a 1 or a 0 depending on whether an elephant is inside. And we see that with lots and lots of other use cases. There's lots of stuff that we as humans can very easily perceive, things that happen in the world. Anything with motion, like, am I currently on a car or am I on a train, depending on like how I feel. I can probably figure it out if I'm the person sitting up there. Do I hear glass breaking or elephants making sounds or anything else that's happening all around me? Or do I visually perceive certain things? Really easy to see that as a human, but really, really hard to program into our IoT devices because there's not a off-the-shelf sensor to do exactly that. And that's kind of unfortunate, because for me, that is where the interesting part is. This is why I, 10 years ago or something, got into the Internet of Things. I figured, well, once we have all these billions and billions of devices shipping every year, all of a sudden I can really understand the real world out there. But for that, I need to be able to perceive lots of stuff that I currently can't easily sense with the sensor that we today have. But that's kind of that, you know. I think that's a very interesting way that we can move our IoT deployments to much higher value use cases. Once we can start perceiving everything that we as humans can perceive, but in an automated way, that means we can solve much more interesting problems, and thus increase the value of all the deployments that we have. Now, naturally, there's a reason why we don't do that, and that's, well, first of all, it's really hard to kind of understand really complex signals. Think of all the sounds in the world that you can hear and try to distinguish when glass is breaking, and then write an algorithm to actually do that. It's insanely hard because of the infinite amount of possibilities all around us. And then there's a sheer amount of sensor data that comes in when you want to analyze something like that. Even if you have an accelerometer, for example, that does fault detection on a motor or on a machine, and you want to know when something starts to break, even if you just look at the raw stream of data that an accelerometer is able to gather, it can be maybe 100,000 or maybe 1,000 times a second, or a bit less depending on what you want. But let's say 1,000 hertz accelerometer. These are things you can buy for $2 these days. Imagine just the sheer amount of data that comes from that sensor that we then need to process on the edge itself, because we can't really send all of that data straight to the cloud, because, you know, we probably have bandwidth and cost constraints of doing that. And thus we kind of throw that away. Even if we have a really nice accelerometer these days on our IoT sensors, we probably just take the peak motion, the average motion, and we ship that off once an hour somewhere to the cloud. So we have cost, bandwidth, and power constraints on our devices. And that's why we kind of don't do much with all the data that we really gather. Let's tackle that. I mean, that's why we're on this webinar. Let's see, how could we tackle that? So how I like to describe machine learning is just another way of writing your software. And it's a way of writing your software in case when you know that there's a correlation between your data and what you want to get out of there. And that correlation could be, I know that there is a certain waveform, audio waveform, that I know has to do with breaking glass. But it's really hard for me to write an algorithm that looks at any possible waveform, a second word for audio, for example, and then write an algorithm that tells me, yeah, I hear glass breaking, or no, I don't hear glass breaking. So if you have a problem like that, where you know that there's a correlation, you know that you can probably figure something out that maps that input to the outcome, but you don't know how to write these rules, machine learning can help. It's not a magic black box, it's an engineering tool. But an engineering tool that lets you rephrase your problem in a way where you say, rather than I have inputs, my sensor data, I have my rules, my business logic or my control loop, and that gives me the outcome. Rather, you rearrange this and you say, well, I have the inputs, I have my sensor data, I know what the outcome should be, help me find the rules. Really interesting way of thinking about it, I think. That is really cool. And this allows you to kind of start analyzing lots of really messy high resolution sensor data. Anything around recognizing sounds, do I hear glass breaking, do I hear a cat meowing, anything like that. Biosignal analysis, based on your heart rate, do I think that you're in deep sleep? Do I think that you're getting, or that there's a chance that you have COVID, all that kind of stuff. In industrial equipment, can we detect abnormal vibrations on a machine? Maybe not even on the same machine, but compared to all the other machines in our factory. And then that's really cool. The Himax board has a camera on it. We can even start doing image classification. Really awesome. So yeah, most important line kind of here. Machine learning is really good at anything with really messy high resolution sensor data, where you know there's a correlation. You know that there's a mapping from input to output, but you can't find these rules by normal programming. That's something where machine learning really can help. Now, if you're watching this webinar, you think, well, Jan, yeah, really interesting, machine learning, fantastic. I totally sort of believe you, but how can we actually run it on small embedded systems? I mean, I thought machine learning was really the domain of this, like a large data center full of GPUs crunching numbers. So let me give you a little example of how someone can actually build an ML model and how we can scale it down to something that runs on an embedded system and why that even works. So just say it's really just another way of writing your control loop. Rather than having your rules and your input and your rules and an outcome comes out, you let the machine figure out the rules. And you do that by providing lots of data and lots of outcomes that you think you should do. So let's write an algorithm to detect whether water is boiling. So I start out, well, I need a temperature sensor, and I write a very simple control loop. If the temperature is above 100 degrees Celsius, boiling temperature of water, then yeah, water should be boiling, otherwise, no, it shouldn't be. So I write this out, I create a little POC, and I deploy that here in my kitchen. So I try this out, I'm like, well, I bring the water temperature to 102 degrees. According to my algorithm, yeah, it should be boiling. I observe it is boiling indeed. Okay, great, cool. I do a sanity check at 98 degrees. According to my algorithm, this water should not be boiling. I observe that it's not boiling either. Really great. But now we go mountain climbing. We add a second variable. So now we go mountain climbing, and my temperature sensor still reads 98 degrees, and I'm at 2 kilometers high, a mile high. And now, according to my algorithm, the water should not be boiling, but I do see that the water is boiling, and this leaves me very confused. Apparently there is a hidden correlation between temperature, altitude, and whether water is boiling, yes or no. And to uncover that hidden correlation, that is a place where we can then attach machine learning to. So rather than trying to figure out these rules by hand, in this case, relatively easy, right? We only have a few variables, so we can figure it out. But think of an audio signal with 16,000 samples a second. Rather we say, well, I have my base data, my sensors. So I have my temperature sensor, my altitude sensor, and I have the outcome, what I want. I'm just going to collect this in a large Excel sheet or wherever I collect my data. And here are my inputs, my data, the two sensor values, and then the ladder is my label, the outcome, the preferred outcome. Now, everything that a machine learning algorithm does is it just finds a function, a mathematical function, that most accurately maps this data to that label. And that takes lots and lots of trial and error because the machine learning algorithm has no idea what temperature or altitude is, or even what boiling water is, yes or no. And it's also really important that the data that you collect is really clean, because that's the only thing that I can work with. It can't reason about it, say, hey, I see a temperature of 110 degrees at altitude 0, which is labeled no, water is not boiling. It can't say, hey, this is illogic or something. So it's really dependent on the quality of the data. Takes lots of trial and error, but what we get out of here is just a mathematical formula. It's just mathematics. I probably get something like this. This is how you do the boiling temperature of water with the temperature and altitude. And there's no difference between me finding this formula myself and writing it out in a control loop, or that the ML algorithm finds those rules for me. No difference. It's in the end, it's just a mathematical formula that we find, and it helps us uncover that correlation. So think of this, machine learning is nothing special. Yeah, it takes lots of effort in finding that hidden correlation in case you can't find it yourself. But afterwards, this machine learning formula is just mathematics. That's it. And computers are incredibly good at math. Even small MCU type of devices, Cortex M4, for example, from ARM, is capable of doing 40 million operations a second. An astonishing amount of compute. So if you know that, and yeah, it's kind of an important thing here is that if you know what hardware that you want to run this on, you can set constraints on this formula already from the beginning. You say, hey, I need to run this on, well, the Himax WE-I Plus dev board, so I know the compute capabilities of the device. So I'm not gonna, the formula that I say, the number of parameters that can be in that function, I'm already gonna limit beforehand, and I let them find the best approximation of this function. And that's really cool. And that means that I'm going to find the best formula to map this input to the output within the constraints of my device. We've seen that we can do an astonishing amount of things on this because of this. So we have, yeah, this little dev board. Sort of in CK will tell a little bit more about it, but this little dev board, it's about the size of a coin, is able to do real-time vibration analysis, real-time audio classification, real-time image classification. It's absolutely amazing. And that's just because we know how to design with constraints in mind. So cool, that brings me to Edge Impulse. So Edge Impulse is founded by me, co-founded by me, together with Zach Shelby. Both of us used to work at ARM, and we're engineers. And we're building a tool from engineers for engineers. I kind of see it as an IDE for helping you build these types of machine learning problems. It's really the place to do anything with machine learning and that needs to run on device. So we don't do large things on just data. We focus on sensor data. We help you do data collection, designing a machine learning pipeline. It doesn't have to be just ML. We do signal processing as well. You know, the easier the better for us, and then help you do deployment. It's free for developers with over 50,000 real ML projects already created, literally from anything from a camera trap on the African savannah that detected elephants going about. Someone did a Lego brick sorter. We see all kinds of magic wands and people do kind of imitate Harry Potter style things with this. An electronic nose that can sniff whether it's whiskey and what brand of whiskey is in your glass or that it's rum. Like a really wide variety of really super interesting things. So you're going to see this in a little bit. I think it's really cool. But here's the reason why we do this today with Himax, and that's we have great software, I think, that really lets you build this, but we also need to pair this with some really great hardware, and that's why we brought Himax in today to tell a little bit about the WE-I Plus. I've worked with the platform now for the better part of 6 months. I really like it. So CK is going to tell a little bit about the platform and what it can do. CK, take it away.
Thanks, Yang. Now I will introduce WE-I Plus EVB platform. It's a very tiny platform. The size is only 40 millimeter by 27 millimeter. And on our evaluation board, you can see we have Himax WE-I Plus MCU. And also we have on board Himax HM0360 AOS VGA camera. It also a product from Himax. And we also integrate FTDI USB bridge chip on this board, so the user can easy to connect to our board. Only a USB cable needed. And the LED power supply already on board, and we have accelerometer and the microphone, so we can run micro vision application, micro voice application, vibration application, and all the example already deploying for use. So also we have some expansion header. We have I2C and GPIO. So if needed, you can connect to temperature sensor and the other sensors. So I think this is a perfect platform for tiny machine learning. And the next page. I will introduce our WE-I Plus AI processor a little bit. We embedded ARC EM90 DSP, and the frequency we can up to 400 megahertz. So it is very high speed for MCU. And we also have XY memory. It's multi-bank memory architecture. So it's very useful for the machine learning inference. So our throughput is much better than others. And we have some image accelerator inside our chip. We have motion detection and the 2x2, 4x4 filter. It can do scale down and the mosaic for color image. And we have JPEG codec, HOG extractor, and the resampler. We also have some computer vision application. And we have multi-layer power management system. We only turn on necessary circuit power when during the operation, so we can reach ultra low power entire system. And we have 2 megabyte internal memory. It's large, so we can support up to VGA image application. Also, we embedded hardware security engine in our chip, so we can support security boot. It can protect your software and your algorithm. And also we can support secure communication between WE-I Plus to SoC or the cloud. So the message communication will be protected. And we have comprehensive peripherals. We have camera interface, so we can support image application. We have I2S and PDM audio interface, so we can support audio application. So this is the special of our chip. Yeah. And the next page. Right now, the version 4 already available on smartphone website. So if you're interested, you can purchase one and enjoy the tiny machine learning, especially with Edge Impulse system. You can develop your own algorithm very easily. Thank you, Yang.
All right, thank you, CK. Yeah, and I think the last thing that CK said here is really important. Like building machine learnings really starts, building ML models really becomes beneficial when you actually do it with your own sensor data, because then you can apply it to your specific domain knowledge. And that is where this stuff becomes really, really, really important. So as CK said, we have an accelerometer on this board, 2 microphones and a camera, and all of those are supported in Edge Impulse. So you can build models that detect weird vibrations on machines. You can detect stuff that responds to your voice whenever you want to say hi Jan or hi Max or whatever. You can light the camera up. We can have the camera models doing a wide variety of things and actually running in real time. So we can run about 10 times a second doing a 96 by 96 pixel image using one of our transfer learning models sitting in Edge Impulse. And it's completely integrated in Edge Impulse, so you have super easy data capture from all of these sensors and really easy deploy as well. We're going to see in the demo. So yeah, getting started in under 60 minutes, I guarantee that. If it takes you more than 60 minutes, find me next time, I'll buy you a beer. Get the board from SparkFun, sign up for Edge Impulse, and then follow one of the tutorials on doing stuff with the accelerometer, microphone, or camera. Really easy. If after this webinar you think, hey, this is really cool, I'm going to order this dev board straight away, but you don't have it in yet, everything that I'm going to show you, you can also do with your phone. And that makes it really easy to do some data capture and do some initial validation of your ideas, and all of that stuff. Even the complete data set is then transferable to the Himax board afterwards. As said, docs on all of this stuff, end-to-end tutorials with nice videos. Here's Dan Sitaniake. He's the author of the TinyML O'Reilly book. He works for us as a founding TinyML engineer. He has done the one on audio classification, super smart, and we have a wide variety of tools for basically anything here. And I think the cool part for me working in kind of the tiny ML, the machine learning meets IoT industry for a while, is that once you let the engineers really develop ML algorithms for their use, that gives them really superpowers. Because no longer do you need to say, hey, I need to go to a data scientist and I might have an idea of, you know, what I can do here, but rather you can start collecting your data, verify whether what you try to do actually makes any sense in an hour or two, and from there actually start working. It's still an engineering process, right? It's not a magic black box where you throw a bit of data in and you get a model out, but really start engineering something that has machine learning in it. And my strong belief is that every product or every engineer 5 to 10 years from now will have machine learning under his back. Not something that you'll use for every project, right? But something where if you have a problem where it makes sense, where you try to find this hidden correlation and you can't really do that, machine learning is just one of the other tools under your belt that you can use, similar to how we do signal processing to do sensor analysis today. So that's the thing when we really start to give superpowers to our engineers. So with that, I am going to jump out of this presentation and to the really interesting part, which is our demo. So I'm really looking forward to that. Cool. So I have the Himax WE-I Plus dev board here. There we go. Really nice little dev board. So we built a small firmware application for this dev board that helps you with data collection. So once you have that, you connect it over USB. You run the Edge Impulse daemon. It connects to a project, and now you're ready to start doing machine learning with this board. That was really easy. So Edge Impulse is free for developers. Just go to edgeimpulse.com, sign up, and then you'll be taken to a project. And a project is a place where we acquire training data, where we design impulses. And an impulse for us is kind of a combination of signal processing and machine learning pipelines. You train your models, and then finally you can deploy that back to your dev board. So let's see how that looks like. So I have a project. So first, not completely visible, but here on the right for me is a piano. I also have a lamp, and I want to train a model that can start distinguishing between a number of things in my living room. This is super widely applicable. We have customers doing the same actually for doing banana ripeness detection. How ripe is a banana? Detecting whether stuff is broken or not, whether screws are actually screwed in or not on a factory line. So very wide. So you have a multi-class problem. In this case, the class is either I'm seeing a lamp there, either I'm seeing a piano there, or I'm seeing a plant, which is all the way in the back. Or I'm seeing something completely different. And that last thing is really important. A machine learning model has no idea about what the world is. So you need to give it kind of examples of everything. And we only have 133 items here, 133 photos, so easy to do. Very useful. So I have my Himax cam. I'm going to set it to a bit lower res. I have a camera feed here. So you can see me live from the board, which is really nice because you don't really know what you're pointing at normally. So let's add a photo of a lamp. That is my lamp. We take snapshots, we pull it in through the USB interface, and there we go. Now I have a photo of a lamp. I'll add one of my piano. Cool. And then I need, something that is neither a lamp or a piano. So take a quick view of my living room. And cool. And this is how I really quickly build up this data set. So I have about 136 items of data. That's literally anything from my piano from a couple of angles. I made a couple in color, a couple in grayscale. So the Himax camera has a monochrome sensor. But it's fine if I snap my photos in color because we can reduce the color depth while we're building this model. So with that, let's actually design our impulse. So the first thing is that we want to normalize kind of all our data. So that's first setting what is actually the size of the image that we're going to be looking at. Here we're going to be looking at the 96 to 96 pixel image. Might not sound a lot, but you can see a lot of things on that already. And it really helps with the speed and memory usage on the device. We'll have a pre-processing block In this case, we're just going to reduce the color depth to 8 bits, but you can plug in all kinds of stuff, face detection, algorithms, etc. This is completely codable by you as well. So you can say, hey, I want to add something new, a custom block, and we'll have a whole tutorial on actually how to do that. And then we want a machine learning block. So in this case, we want to learn from this data and classify that. And the one thing that is interesting here is that for lots of image models, if you train a neural network, just a fancy way of describing this really large mathematical formula where you map the inputs to the outputs, is that these networks learn a bunch of basic things first. And that's the same in almost every network. So that's stuff like contrast between things. Then you start learning basic shapes, and you slowly build this up. So we only have a bit over 100 photos, which is normally way too little to train an ML model. But by training first a really large model on lots of a variety of different things, then stripping off the top layers and replacing that with your data, we're able to build really well-performing models with relatively little data. So that's something we have. If you want to have a neural network from scratch or a different ML model, you can just click here, add something here, and start hacking it straight away. So cool, let's look at our image. Well, as said, the only thing we do is actually normalize this to 96 by 96 pixels. So we cut off the sides here if needed, and then we map it to grayscale. Not a lot to see here. The interesting part though, and something that is really fun to show, is that after you do this, we can show a visualization of your complete data set and give you an indication of whether we think your ML model is going to work. And that's our feature explorer. So this shows after the normalization and after the bit depth reduction, your whole data set in one 3D graph. And if this data separates nicely, which you can see, like there's a green cluster here, there's a green cluster here, the orange cluster is nice separated, that means it will probably work fine. If there's stuff that is intermixed quite a bit, this blue one, this looks a bit weird. That's because it's from the other camera, I guess. Then it might be an indication that there's something with your data set. So it's really easy, quick way of actually finding interesting potential issues with your data set and how well we think your data set is going to separate. Cool, in this case, looks nice. We'll show you on-device performance at any point as well, including the size of the operation as well as the speed that we think it is. And we do this for all kinds of signal processing things. I'll show an audio project in a little bit. And from there, we can train our machine learning model. So we're training a neural network here with one of the transfer learning models. So I did that already. Cool thing here is that we have the same feature explorer again, but now we actually show which items were classified correctly. So where did the ML model get it right and where did it get it wrong? And that gives us really quick insight in our data set quality. So, we're almost completely right. 96% accuracy is really good, but there are 2 dots here that are marked in red. So let's actually click on one of these. And here's an issue with my data set. So I labeled this photo as unknown, but because I probably was doing something with my phone, moving it around fast, I accidentally put the lamp on here as well. So the ML model actually says, hey, I predicted this is a lamp. It is indeed a problem with my data set. And we can flag it this way, jump back to the view sample, and then delete that from my data set or relabel it to build this model up quicker. We also do a bunch of optimizations here. So to make this stuff run faster, during the training, while you're building this ML model, you have this really large mathematical formula that we constantly need to refine the training process. So that is done typically in floating point numbers, but that's pretty wasteful, right? We have lots of parameters. This function is really big. So one of the things we can do is say, well, after the formula is trained, we reduce the accuracy in the model to int8 accuracy. So we go from 4 bytes to 1 byte per activation or per kind of formula little piece in there. And that means that we can run a lot faster on device because we can push much more operations in. So you'll see that the unoptimized version needs about 500 milliseconds to run on the Himax board, while the quantized version actually runs in about half that and uses a lot less RAM. So kind of cool. Okay, we have a model. Let's test it out. So once again, I can go here. I can point it to myself. let's take a look and see what it thinks I am. All right, so it thinks that I'm neither a lamp, a piano, or a plant. I am very glad about that. Let's actually look and see if we can do something if we point it at another object, how well that works. So that's a lamp. All right, so this ML model seems to work quite well. Now, naturally, this still runs in the cloud. So let's take it offline. So when we head to the deployment tab, there's a couple of things we can do. If you want to integrate this into your own project, you can deploy as a C++ library. This will give you all the signal processing code, all the ML code, all packed together in a single library. It has no binary components, except for a couple of things in the Himax dependencies, but we try to ship no binary components, and really easy to integrate in your final firmware. So we have lots of examples on how to do that on the Himax board, because we want you to not just run this on a dev board and try it out once, but rather actually deploy this into the field. I think that's where really the value is. So really straightforward. Or if you have the Himax board, you can just say, hey, click here, and we build a full binary for you that then runs on the board. So you can quickly evaluate whether the model is going to run on device, yes or no. So we hit there. I can hit build, and that will give me a binary file that I can then flash to the board straight away with a couple of flash scripts. Really nice. So for the sake of time, I've already done this on the board itself. So let's actually go take a look and see if we can get something on the device. So after you flash the binary to the device, I can do run impulse. And this will just snap a photo every 2 seconds and tell me what it thinks it is. So what you get out of here is a prediction. So we think we have 0.92 confidence. It's not really a percentage thing, but think of it that way a little bit. That we're neither a lamp, piano, or a plant, which is correct. It's pointing upwards at the moment. And we give you the time that it took. So analyzing a full frame here on the Himax, which is just a DSP, we can do in 132 milliseconds, which is incredibly fast. So let's try this out with some other stuff. So there we go. Let's point it at a lamp. There we go. Lamp. Let's point it at a piano. Cool. Piano. Let's point it at Jan. And a noun again. So really nice. However, there's one thing that we're going to. So this works, but as you can see, there's a couple of places where we're in transition state, like we're moving the camera around, and it might be that the model starts classifying things incorrectly because of that. So we don't want to just trust a single frame typically. So let me show you how easy it is to integrate this library in your own application, and now we can add a little bit of smoothing over that signal to be more confident in actually what we're looking at. So we put this page together. It's on the docs. And that contains references to example applications, just normal code, resources on it, how to connect, etc. And part of that is that we have a repository for this board written in C++. You can build it on any platform, free compiler as well. In here, I can write a little bit of extra code to do things depending on what I see. So here is part of that application. And to do something with this board, the only thing we need to do is say, capture a photo. Step 1, capture a photo. Then we run the classifier. We just say, okay, with this data, with this photo, tell me what is there. And that structure, the result structure, basically gives me the confidence for every single one of those classes. So I can do stuff like loop over all the predictions. Let's say that if my piano is 0 and my confidence is above 0.8, I want to send something to the cloud. Really easy to integrate this in your firmware. It's just like a drive, but rather than giving you raw sensor data, it just lets you do something there. Or we can say, well, I want to smooth some stuff over. So here we say, well, look at the last 10 readings. And when 7 of them are above 0.8, then I think that something is happening. And then you just get the prediction out. And then we print it out. So really nice, just a couple of lines of code to integrate that into your normal projects. Let me run this in continuous mode, so you'll see that happen. So right now it's kind of pointing down, so it's unknown. I will point it at the lamp. It will take a little while, right, to stabilize now, but we don't get any false positives anymore. So insert then while it's jumping. And there we go, looking at the piano. And back to unknown when it's pointing at me. So really nice and quick. As said, you can't just do image stuff here. We also do vibration and audio models, and with the GPIO headers, you can basically plug in anything into this board. So we have cool tutorials. Here's, for example, one where we train a keyword spotting model with people saying, "Hello world." You can't hear that. So once again, we collect data, noise data, unknown data, so stuff that is not hello world, and then hello world itself. The whole tutorial will help you split this data out and collect this really easy from your Himax board. In that case, we actually train a signal processing pipeline first. I love signal processing. It's really explainable and often much easier than a neural network. We'll give you this full feature explorer again, and here you see nice separation between hello world in blue, wrapped around basically noise and unknown. So this is going to work quite nicely and help you train an ML model and evaluate that ML model here as well. And once again, really easy to deploy this to your Himax board and evaluate that way. So yeah, with the demo, I like to jump kind of to the recap in the last 3 minutes, and then we'll open up Q&A. First and foremost, the machine learning hype is real. It is an incredible engineering tool, not a magic black box, to solve things and to find correlations in data that we could never have done before. So any place, any time where you think, okay, well, I have lots of data coming in, but the only thing I can kind of do is write a small thresholding control loop, see what we can do. Machine learning is able to pull correlations out of there that you might not see directly yourself. Don't treat it as black box either. You know, use signal processing wisely wherever you can, and then apply a little bit of machine learning on top. But then it's incredibly powerful engineering tool. Really makes you help see the world around you. I also think that machine learning and sensors are, because of that reason, a perfect fit. If you look at where we come from sensor, on actual sensor hardware, we've done a tremendous job as an industry in the last 10 years, right? We have MEMS sensors now that are super tiny, incredibly sensitive, and really easy to put on a PCB. But they deliver so much data and at such high frequency to our MCUs that it's often very hard to actually draw conclusions from there. And machine learning really helps you unlock that. And that's why I think that is absolutely perfect. And together, yeah, I think that this really has the potential to make our IoT devices a lot more useful by teaching them to feel, hear, and see the world around us. So I recommend everyone after this webinar at edgeimpulse.com, sign up, grab a Himax WE-I Plus EVB, or just use your phone to test the waters and start building. I think you're going to find it incredibly useful and probably find a fantastic use case already in a product that you're currently working on. So with that, thanks, and I'll hand it over to Max for Q&A.
Well, thanks so much, Jan and CK, for an excellent presentation. I personally buy a lot of things from SparkFun, and I think I can see a Himax WE-I Plus in my future. So now we'll get started with today's Q&A session. And I want to thank the audience for their participation. We've got questions flooding in on my left-hand screen. And we'll do our best to get through all of them in the time remaining. During our Q&A session, I'll leave this screen with contact information for today's speakers, should you wish to get in touch with them following the webinar. Okay, let's get started. Question 1, How will the IoT help in the digital transformation to Industry 4.0? And are awareness of the IoT and its importance necessary before implementing it in industrial environments and organizations?
That's an interesting question.
Yes or no?
Well, yeah. So actually, I think what an interesting observation that I made. I don't have a perfect answer to this, right? And I think there's no perfect answer here. But one of the interesting things I saw 2 years ago at Hannover Messe is that the thing that I've kind of seen is that IoT is encapsulated a little bit by Industry 4.0. I think lots of startups, especially 10 years ago or so, thought, okay, this IoT thing is fantastically and super cool, and they started building IoT platforms and really thought of IoT as one thing. I think that we succeeded as an industry at the moment in making kind of what we call IoT, connected devices and stuff, so widely adaptable that it's now being a real fundamental part of lots of other industries. I think that's where Industry 4.0 kind of kicks in. All the same things that we thought were important, connected devices, security, updates, streaming data over the internet, that is now a fundamental part of that. But rather than owned by IoT companies, it's owned by Industry 4.0 companies like Siemens. Which I think this is how we succeeded, right? If you look at the number of MCUs that ship, the 30 billion devices that I had on one of my first slides, this fucking revolution has happened already. But now that it's mainstream, we don't call it IoT anymore. It's just part of something else. I think that's where kind of these two worlds collide. I don't know if that's completely answers the question, but that's kind of my take on it.
Okay, yeah, no problems there. Can we run MobileNet FSD models on Himax?
FSD, I don't know what an FSD model is. If someone could answer that. What we can do today actually is MobileNet classifiers. So we train them with a lower alpha to reduce the feature space, which works really nicely for us. And there's a number of models you can actually choose depending on the latency and RAM constraints that you have. Like the Himax one is really powerful. You can basically run anything on it, but you might say, hey, I need to do this 20 frames a second. So in that case, you can choose one with lower alpha. And we are coming out probably by the summer with some object detection models, not based on MobileNet, but real object detection or object tracking over live video on these types of devices. But my pet peeve always is you probably don't need object detection. As you can see, I can already track stuff in my living room just by normal image classification. I think for lots of IoT solutions, that is that works really well too.
Okay, here's an interesting one. With the Himax board and Edge Impulse, is there a way to automate the image collection? For example, watching a door with the camera and then having a door sensor trigger the capture. Could I leave this running for several days to capture the photos?
Yeah, it's how do we do it with yeah, there's two ways of doing that. You can either say I connect this device with a little Linux host or something to it that relays the data, and then send the capture request whenever the door sensor triggers, and then we upload it automatically. Other than that, the whole protocol is open. So if you rather have a better idea, if you want to store it on or on some of the internal flash or connect an SD card over the extension header and write the files that way and upload them at a later point, that's fine too. You're kind of free in doing that. But our API is flexible enough to trigger on certain things and then trigger a capture.
Cool. Okay, in your example, you polled the camera every 2 seconds. What is the fastest realistic time you could sample the camera? 1 second, half a second?
So at least in the second demo, we do 137 milliseconds per inference. So that's 8 frames or so. CK, do you know how fast we can get data from the camera? What's the FPS?
The camera capability, we can up to 30 frames per second. Yeah, the hardware capability. So, and we need to consider the transmission time and the storage. So it will depend on the resources we have. For example, the image size resolution. Do you want to resize to larger or smaller resolution?
Yeah. So combination, this can be much faster than the 2 seconds. The 2 seconds is just a quick demo, but we know that we can do 8 frames a second, even at 96 to 96, including classification. And if we put a smaller model, I'm pretty sure we can push it to 20 frames a second, including real-time classification, which is almost video classification. It's pretty insane if you think about the class of device that can do this now.
I tell you, I'm blown away by the stuff we can do today. How large is the C++ library? Does it grow with the complexity of the problem? And do you need to store all of the images on the device?
So for the first one, yeah, so this really grows with the complexity of the model. We always show you on the deployment tab exactly how large it's going to be. So the model that we were looking at just now is 235K of RAM, 297K of RAM, and 577K of ROM. But naturally, this is because we have lots of stuff to work with on the Himax, right? We can do this much smaller. So we have this stuff running on if you go for a smaller model and a smaller image size, you can do this under 100K of RAM. And for other stuff like audio and vibration models, you can push that even under 20K of RAM, depending what you want. So, and we give guidance at any point. So if you change one of the parameters, like I want to use a different FFT length in my audio pipeline, we'll show you immediately what the effect is going to be, both on the RAM and latency consumption on the device you're choosing. But the cool part, one of the coolest part, I think, of what the Himax thing does is there's so much RAM to work with. It's amazing.
I know. I remember the days when you could buy an entire computer. The single board computer, it had 1K of RAM.
Yeah, yeah. So the smallest that we can go right now is on our vibration models, and that runs even on a 16-bit MCU in 6K of RAM. So,
wow. Right, a more technical question. For images that are not square and a data set that includes images with mixed heights and widths, which option is best for the DSP? Squash/longest, slide/shortest, etc.
Fit shortest, because that's what we do on device. So in that case, we look at the shortest axis, we look at the size that you want to go, and then we cut piece part of it off. That typically gives the best results. But yeah, as I said during the presentation, dataset quality is really important in how well your model is going to work. So having a wide variety of widths and heights and color depth, etc., in your dataset typically is an indication that you could do a little bit better on the data collection side. But we try to make it as easy as possible. But use fit shortest for now. Okay,
we've got two related questions here. One is, did you try the ML libraries on other platforms like the Cortex M4? And then the other one is, which ARM Cortex architectures do you currently support?
So we support all the Cortex M series, M0, M0 Plus, M4, M4F, M7, M33. I'm coming out with M55 support soon, with full hardware acceleration on the M4F, M7, and M33. Yeah, and naturally, so on the Himax board, we have full hardware acceleration for the ARC DSP. But what we output is just mathematics, so it runs on everything. We just load optional optimizations depending on the platform if we can do that. So using the vector extension or using the DSP on the platform. But the source code of the library is plain C++. There's nothing to it, and you can compile it on anything from a 16-bit microcontroller to a Linux box if you want.
Actually, that leads to the next question, which is, will you also support Linux-based hardware with CPU/GPU grade processors?
Yes, coming in April.
Which year?
With full hardware acceleration. They had this year.
Oh, okay. I got caught that way once. Yeah, someone said it'll be ready by Christmas, and I neglected to ask which Christmas. Could you please discuss how collected data is sent to the cloud?
So there's a little, so the device connected over the USB interface that CK said. So there's an FTDI chip on there. So we have a little daemon running on your computer, And when someone says, hey, make a photo, we talk to the board. We say, hey, make a photo, AT commands. The board sends the buffer back, and then we transmit it over HTTPS to our ingestion service. So there's a little daemon running on your computer.
Okay.
So I have a question actually for CK. Maybe that's interesting. Sorry for hijacking your thread, Max. So the dev board is $65, right? If I want to productize this, and I want to buy the WE-I Plus chip and the camera, what would that cost me?
The cost?
Yeah.
Right now we are working on online sale for the chip and the camera module. Yeah, but we're still working on it, and I hope we can make it available online selling for some small quantity to the developer. Or you need to contact our Himax sales team to purchase. So online selling is very interesting and useful for the early developing. We are working on it.
Okay.
Okay,
Cool.
that does lead to another question. Is the hardware and software open source?
I'll leave the hardware question to CK.
The hardware, our schematic is also published in a website, so you can see the schematic and develop in one circuit for your prototyping. The EVB we just showed today, the schematic is open, and the BOM is also available.
Cool. On the software side, so at least the firmware that we built, all the device software, we open up as much as possible. But there are a couple of binary parts that we get from Synopsys that we can't share, unfortunately, here. But you can take a look at that and modify that as well as licensed under the Apache 2 license.
Time for one quick question. You had to hold, and I'm sorry for all the people that's still coming in, but we'll get to that in a moment. You had to hold the camera on an object for quite a bit. How well can the detection occur on a highly transient object passing by?
Yeah, so I think CK, so actually it can be really fast. So the reason why we added a bit of delay is because I want to reduce the number of false positives, kind of triggering. But as CK said earlier in the diagram, there's a way that you can trigger on movement on the camera, snap a photo, classify that immediately, and then you'll have that straight away. So it was just for safety checking here, but there's no reason why there has to be a delay in there.
Awesome. Yeah, we're trying to leave people with like 30 seconds between the end of this call and the start of the next video call, because everyone goes from one call to another these days. So thank you so much. Those great answers to some great questions. For those of you who posted questions that weren't answered, we're going to forward any remaining questions to the Edge Impulse and Himax teams so they can follow up with you later. As a reminder, this recording will be available for on-demand viewing starting tomorrow, where it will be found on IoT Central at iotcentral.io. And that brings today's webinar to a close. I'd like to thank everyone for attending and for your thoughtful questions. And a special thanks once again to Edge Impulse for their sponsorship, as well as to our presenters, Jan and CK, for their insights into today's topic. Once again, this is Clive Max Maxfield, and I'm pleased to have been your host for today's event. I look forward to seeing you all again on the next IoT Central webinar. And until then, from all of us here at IoT Central, we hope you have a wonderful rest of your day.